Alright, this time in this video I want to show you how to reproduce the exercise already done in this video, Ansys Fluent tutorial solid to fluid heat exchanger. This guy, well, he did very well, but the only thing was this video, well, the original video is confusing because some parameters in the boundary conditions like the interface, well, not many people understand how to do that, and how the original video shows is something that, well, I don't know why, but that doesn't happen with the rest of us when we are trying to do that. So, well, first thing to do is to just start including the analysis system fluid fluent. So let's do that. So let's start with the geometry. So new geometry. Well, meter. Well, I'm gonna use meters, and let's start the file, import external geometry file. So I'm going to just import parts like bodies from SolidWorks, not like assembling or something complicated. No, this is simple. Just two parts. Only you have to know that, well, the location it has to be, well, in the same place that the, all the parts in your assembly will fit correctly, you know. So then I'm gonna import first of all the fluid. This is just a cylinder, you know, the fluid, because, well, it's water. So let's generate it. It won't take much time. It's an easy model, I guess. So it is creating now. Alright, now you can see this, and we can choose at this very time that this is fluid. Let's do this because that is important. You have to do this fluid, not solid, fluid, because this is the water, the model of the water, the representation, you know. Then, well, now let's import the solar plate. So the solar plate here will be this one from SolidWorks also. Generate it, and you will be able to see that both bodies will fit together perfectly, because that is very important. Yeah, you know. Then you can see here, I can choose here, or I can choose the other, and I'm gonna show you. Yeah, well, there's something here, I don't know why, because this is it's solid. But to differentiate it, I'm going to select this and say add frozen and generate. I don't know why, but this works very well. Now you can see both bodies here, both parts. So let's continue, generate it, and that's it. We have both bodies here, and that. So go ahead. Now that this is update, I'm gonna start meshing. Okay. Well, this mesh, I'm gonna select some parameters here to improve my meshing, like the relevant center I will put fine. In the smoothing I'll put high. Transition I will leave slow, and span angle center fine is good, I think, and we're gonna see how this improves from the original video. In the nodes and elements, amount of nodes and elements that this system creates. So let's see, generate mesh. It'll take some minutes, I don't know, some time. Yeah, it was really fast. And you can see nodes 88,000. In the original video it was like 70,000, I think. It's okay. We have good machine. Then we're gonna continue. Now to continue, we have to just like we need to create the surfaces. We have to define them because that is really important when we are using Fluent, because when you have to create the boundary conditions, you have to select and you need to have some defined surfaces to create the boundary condition and to define them. So let's create that. First of all, let's use, well, oh, I forgot. Sorry, I'm gonna go back because I forgot something important. In the geometry, I'm going to change the names of the body parts because it's better for me, and for example this will be fluid, and the other one will be solar plate. Generated, and that's it. Excuse me for that, but this is some kind of important for me because that will help us later in the setup. So you can see here fluid and solar plate. Now that we have solar plate, I'm gonna suppress the body for a moment while I am creating the surface. Then now this surface, I will call this fluid surface. So fluid surface, you can see here. I'm going to select this and say like this is the outlet. Create name. This is the outlet, and the other end of this bar will be the inlet. Create inlet. Alright, then we're gonna generate the mesh, and we can see here surface, fluid surface, the outlet, sorry, this will be that. the outlet and the fluid surface, and the inlet is in the other end. You can see this here. So you can see the inlet. Now that we have that, we can just change and unsuppress the body, solar plate, and suppress the fluid. And now that we have done that, we can choose here alright. This will be, like pushing Control and clicking. We select 3 faces, and I will call this the top surface, as the original video did. And the other side, I'll do the same, and it will be the bottom surface. Alright. Now what is really important here is the interface. The solar plate interface is something you cannot forget, is this, because without the interface, you cannot connect the fluid and solid, and won't be any heat transfer, any rise in temperature, they won't have contact, and this mesh and all your work will be wasted. So let's create the solar panel interface. So call it, and now, just because it's some kind of important, the 4 sides of the plate, and I'll call this side surface. I don't use the word wall because the system creates some surfaces sometimes, and the system calls it walls, so you can get confused in the Fluent because you cannot see many of them clearly. So, well, I decided to use these words better. So let's continue. Now we have this, we can unsuppress now. Now we have surface, fluid surface, outlet, inlet, top surface, bottom surface, solar panel interface, and side surface. We're going to create the mesh. Now we're meshing. We can update. It's updating, and now it's done. I'm gonna close it. Oh my gosh. Whoa. Wait for the program. And now that you have the mesh, and you can see here that this update, you need to have the mesh updated before starting setup, because without that you're not going to do anything with the setup. You'll waste your time. So now let's continue. Edit. Here it's okay. I think it won't take more than 15 minutes to finish this. So let's put all our energy in this. So the scale, report quality, something that I always do. This is a good meshing. That's what I want. Any more tone quality? It's okay. I think. Now models. I'm gonna use, well, we need to turn on the energy equation and we can leave the rest like that. In materials, we have to delete air and aluminum before calculating because that will create some problems and some conflicts within the system and the results. So, well, you have to remember that. And now we're going to include the fluid we're going to use is water liquid. So let's copy, and the solid will be copper. Just copper and copy, close it. You can close it, and we can see here, and we're going to try to delete it right now, but it is impossible because it's in use. And okay, then cells and conditions, it's fluid. Don't forget fluid, it's type fluid. This always have to be like that. If you put water or oil or whatever it is, you have to be sure that it is type fluid, and the other one is solid like it is here. So to edit fluid, and fluid will be water, not air. It's water for us right now. And just to make sure, I don't know why this is a problem, and you have to look at it. This is porous zone. This has something. This has the aluminum by defect, so you have to change it and then uncheck this and just okay. And solar plate, you have to do just change the material name, and that's it. And continue boundary conditions. This is really important because in all the boundary conditions that it is type wall, you'll see like this. For example, top surface wall. You can see here thermal that you have to change material name for copper. Always you have to do that. And now heat flux. We're gonna see here. These are the conditions from the original video. We're gonna do this, and maybe then we're gonna change the velocity to 0.01, but later after we have the result. Okay, so let's start doing this. And the heat transfer coefficient, no, sorry, this is not heat transfer coefficient. This is, oh yes, this is, but this is a thing. Excuse me for that. So heat flux, it's 800 watts per square meter. So let's put this 800. We're not going to define any other thing here. So just okay. And solar panel interface, yeah, this will have some explanation later. Side surface, it's a wall, as you see. You have to edit this and choose copper. Heat flux, no, this is convection. We're gonna assume that it is like air fluid going through this. because the heat transfer coefficient between copper and air, when the air is over the copper, it is 13.1. At this time we're going to use 15. That's okay for this problem. At this time it's okay, so let's use it as the original video. Outlet. So the outlet, it is from the original video. The outlet, it is okay. You only have to use the general temperature, that it is 293 Kelvin. So the interior solar plate, the interior, all the type interior, you have to leave it like it is. Don't change anything. Interior, it's okay. Inlet, velocity inlet, we will use 0.1, and the temperature 293 Kelvin. It's okay. Fluid surface, this is a wall. We're gonna see this is nothing, because you have to remember we're gonna deal with this later. So thermal, this is a wall, as you can see, is the bottom surface. And momentum thermal, you're gonna choose here copper, and this will have convection with the 15 watts per meter square Kelvin, and the temperature here is 293 Kelvin. Let's do this. Okay, and now you can see, highlight the zone. Now you can see here bottom surface, the fluid surface, it's something, the inlet, oh, sorry for that. You can see here the inlet, right? Then we're gonna see the interior fluid. Sorry for that. Yeah, you can see here interior solar plate. It's all the solar plate. The outlet, that's, you can see there. This is the side surface. It's the side for all the walls. You can see the solar panel interface. That's all the pipe surface, and the top surface. If you imagine, that's the surface over this area. Now we're going to deal with the surface of the inlet and the interface. Okay, now fluid surface, that will be a interface. We're gonna choose type interface, change it, it's okay, and we're gonna leave the same name, because we could have some trouble when we change names, and we can save the program, the project, but then when we want to change anything or try to reopen it later, this will create some conflict in the program, in the system. So let's leave only this name as it is at this step. So this is that. And side surface is a wall, but solar panel interface, that is an interface. That's like that. Now mesh interface, we're going to create a mesh. For this interface. We're gonna call this final interface. Now we're gonna use flip surface and solar panel interface. We cannot select the same surface because this will create an error and a warning message like this: error zone fluid surface selected in both left and right interface list. So as you see now, this is like that. That's what you have to do. Don't choose anything here because that will create problems. I don't know how to use this, but this will create problems. And you can choose draw, and you can see now where it is. Let's create this, and now that you have created this, you can choose, like, push this button, and you can see here something related in the code: interface zone 1, interface zone 2, so fluid surface, so solar panel interface, area, it's alright, and intersection. Here you have a message that those are not created on initialization. Initialization is what you do here in this step, solution initialization. So we're going to there, but right now it's okay, close it. Yeah, now that we are done, we have to delete the materials, the spare materials like air and aluminum. So we're going to delete it and delete it. We don't have problems because we delete it and we put that in this use, so that's okay. Now that we have done that, we have this, it's okay. Solution method, solution controls, solution initialization. Now we have to choose standard initialization, compute from top surface, doing the same as the original video, but now we're going to use this. I'm gonna put 5e minus 4, 5e minus 4, 5e minus 4, excuse me. And temperature, we're gonna leave temperature 300 Kelvin. And initialize. Now that we have initialized, we can see here, look at this. This is what we had when we created the interface, but now we're gonna see what happened after we did the initialization. Interface list, and now we can see here interface wall zone 1 that those were created after the initialization step. So let's continue, close it, and now that we have done this, okay, we can see here solution initialization, it's alright, initialized, it's okay. Every time you change any parameter in this zone, these steps before solution, I highly recommend you to initialize the parameters again, the initial values. And well, let's continue, run calculation. Let's put 300 of the original video, check case, it's some kind of recommendation, but it's okay, it's not a mistake. So let's continue, calculate. It's calculating the solution. We're going to see here the graph. The graph is very similar to the original. Well, and now you can see here, this is the original video. Now you can see here how this behaves. Alright, well, this is not the same point because in the original video at this time, he's using the velocity of 0.01. So well, we're gonna do that after this, but at this time I'm gonna show you the graph and the everything I can do. So we have the solution here. We're gonna see contours, setup, field, temperature. Now we're gonna do this is top surface, and we're gonna display. And now you can see here how this is done. So this is the same graph, and now we can see here 3.12 and 3.93. So that means 312 Kelvin and 293 Kelvin. That's the point here. So we're gonna use the reports, flux, no, the surface integrals, area, weighting, pressure, temperature, and we're gonna choose the inlet and the outlet of the fluid computed, and between 293 and 297. This is the local temperature, and this is the same as the original video did. And you can see here, I don't know why this quality is so poor. Now you can see here this 293, and the outlet. So now we can see this, we can close it, and let's improve this, because this shows us that this is just 4 Celsius degrees between the inlet and the outlet, the entrance and the exit. So that is not good enough, I think. So we're gonna change boundary conditions, so it's the inlet, edit, we're gonna change momentum, we're gonna change the velocity. Now it's okay. Now that we've done that, we can go to solution initialization, initialize it, and now we can do the run calculation and calculate it again. And we can see that this is the graph that is going to be shown in in my simulation. So we can see here, and you can see there, that the white line goes down while the blue line tries to be constant. You can see here how those lines end. And the same with the green and red line and the cyan line. It's something like that. Solution is done. Now you can grab animations, show the top, display, and this. Here you go. This is what happened, and we're gonna see the report, surface integral, compute, and we have 293 Kelvin and 315 Kelvin. So here you go. This is it. Thank you for watching. I hope this will be useful for you. It took really long for me to figure it out how to do this. I tried a lot, so I hope this will work for you. So see ya.